This is screen capture unit 11.3, the third video for unit 3 that has to do with heredity. And for this third video, we talk a little bit about chance events and ratios and statistics. And I don't think this will be too difficult, but if you take the F1 genotypes, you can compare them to a coin. There's a 50% chance that you're going to get one allele, in this case it would be big B, or 50% chance you get the little b allele. It's kind of like the heads or the tails. Heads could be big B, tails could be little b. You have two different coins that you're flipping. One would represent for the male, one would be for the female. The chances that you're going to get any one gamete are 50% or 1/2. So the flip of the brown coin, half chance or 50% chance you get a B, big B, and 50% chance that you'll get little b, or 1/2 the tosses. For the silver colored coin, half the tosses should be big B, half the tosses should be little b, and this would be analogous to the gametes. So big B, take 1/2 times 1/2, and you multiply fractions. You multiply the denominator and multiply the numerator. 1 times 1 is 1, 2 times 2 is 4, so 1/4. 1/4 of the offspring will be big B, big B. Take big B times little b, 1/2 times 1/2 is 1/4. Take this big B times this little b, 1/2 times 1/2 is 1/4. And then little b times little b, 1/2 times 1/2 is 1/4. So each of these boxes represents 1/4, or 25% of the offspring. Now, as it turns out, you have two different ways of getting big B, little b, this hybrid. So you take the 1/4 plus the 1/4, not multiplying them but adding them. 1/4 plus 1/4, and you get 1/2. So 1/2 of the offspring should be big B, little b. You can see the big B, little b here. And 1/4 will be homozygous big B, 1/4 will be homozygous little b. Another way to look at it is to think about dice. Now, a die is what you call 1, and a die is 6-sided. The chance you're going to get any one number when you roll one time is 1/6, or 1 out of 6. Another way of looking at this is, if you consider rolling it 2 times, when you consider rolling it 1 time, what are the chances you'll get one of 2 numbers? Well, since there's 6 numbers you can get 1 through 6, and you're saying that you're going to get 2 of them, that's 2/6, that's 1/3. Or another way of looking at it is 1/6 plus 1/6 is 1/3. And the reason you could say that is here it's one number or the other number. If you're doing 2 rolls and you're asking what are the chances that you get one number and then another number, specifically next time it'd be 1/6 times 1/6, which would be 1/36. Okay, some single gene inherited traits. These are just a few that are mentioned in the text. Dominant traits versus recessive traits, and they're in their respective columns. Freckles is dominant over no freckles. The widow's peak is dominant over straight hairline. The free earlobe that hangs is dominant over the earlobe that is attached. And some people cover their ears where you can't see, have long hair, or cover them otherwise. But if you actually see the earlobe, the free earlobe is dominant, the attached earlobe is recessive. If we take a look at this illustration, this actually illustrates a type of deafness that is genetic, and this was studied on Martha's Vineyard. Martha's Vineyard is an island. It's part of Massachusetts, but it's off the mainland, and it's an upscale island. A lot of well-to-do people live there. I believe it was a smaller island, Chappaquiddick, was off of Martha's Vineyard back in 1968, 50 years ago, when Ted Kennedy drove off a bridge with the young woman that he wasn't married to. But there's a lot of history with Martha's Vineyard. It just so happens, because of intermarrying on the island, that a recessive allele, this what is represented by the lowercase d, codes for a type of deafness. And so there's a type of deafness that historically has occurred with greater frequency on that island. Big D would be the normal gene for normal hearing. So you take two normal individuals that carry the gene which codes for deafness. Those two people marry, and from the male you can get sex cells. Half of them should be big D, half should be little d. Of the eggs, half should be big D, half should be little d. So in the ratio of children, 3 of the children should have normal hearing, and 1 out of 4 statistically would be deaf from having heterozygous parents that have children. Now we understand it's possible to have no deaf children. It'd be possible to have 2 or even 3, but on average 25% or 1/4 would be deaf. 2 of the children would be carriers, and they could pass the gene off to their offspring, and then 25% would not have the gene for deafness. Half the children statistically would be carriers and not show the symptoms. I have a table. This is taken from the text. These are autosomal disorders in humans. These are recessive disorders. Cystic fibrosis, sickle cell disease, Tay-Sachs disease. There's several in here. And then there's some dominant disorders. Huntington's disease, also called ALS or Lou Gehrig's disease. Sometimes that doesn't show up until a person's in their 30s or 40s after they've already had children. Hypercholesterolemia. Some people have high cholesterol levels. That tends to be genetic. Achondroplasia, a type of dwarfism, it's a dominant disorder. I have a picture from the text of a person that's suffering from that type of dwarfism, achondroplasia. And the next thing that's covered in the text, and I should cover in discussion, would be incomplete dominance. This is where, instead of the dominant gene masking over the recessive gene, you take a flower color, such as red and white, and for the offspring that are hybrids, big R, little r, instead of all being red, they're an intermediate in color, they're pink. And this is an example of incomplete dominance. So you self-fertilize this hybrid pink, and you would get 1 red, 2 pink, and 1 white from the offspring. And again, you can multiply those fractions, and you'll see that you get the same thing that you get with a Punnett square or Punnett square, some people call it these square matrices. In incomplete dominance in hypercholesterolemia, you have the homozygous big H, and that would be normal. A person should not have elevated cholesterol levels because they have the correct LDL receptors on the surface of their cells. If they're heterozygous, big H, little h, they'll have mild symptoms, elevated levels, but it wouldn't be as severe as if they are homozygous recessive. That's where they have the severe disease and have abnormal amounts, high levels of cholesterol, and more difficult to control. We also see that there are some multiple alleles for certain characters. You look at the different traits. One example would be the blood groups. And with the different blood types in humans, there are multiple alleles that will allow multiple antibodies to be produced. And O type of blood, that's the universal donor. They have antibodies against A and B, so they can only accept O type blood, but they can donate to any group. And what they're trying to show here is there's no agglutination clotting when you give O type of blood with O. But if you give the O type blood person type A, B, or AB, there will be a agglutination, there will be a clotting of the blood. Type A blood, this is one of the more common types of blood found in humans. The type A blood person would have anti-B antibodies, and so they can receive O blood and A blood, but not B or AB, because AB blood would contain the B antibodies. The B blood type group is less common, and it has anti-A antibodies, so the B type blood people can receive O type blood and B, but not A or AB. Then the ABs can only give to ABs. They do not have antibodies against A or B or O, and they can take blood from anybody, from O type, A type, B type, or AB type. In some cases, diseases or genetic problems are caused by more than, a gene can cause more than one symptom. This is seen with the sickle cell anemia, where the sickle cells are determined genetically, but they cause different problems in different people. Not fully understood, but what they're showing is that condition is called pleiotropy, if I'm pronouncing that correctly. What happens is, in some cases, there will be a breakdown of red blood cells. This causes other problems. There can be clumping of cells and clogging of small blood vessels, such as the capillaries. That causes different types of problems. And there can be accumulation of sickle cells in the spleen, which can cause spleen damage. It just depends on what's happening where in the person. It can be different things for different people, even though it's the same genetic condition. Then there are polygenic inheritance considerations. This is where more than one gene codes for a given character. So far we've looked at 2 alleles, where with polygenic inheritance there can be multiple alleles, more than 2, maybe 3, 4, or more. This is seen with skin color and eye color. And they're showing 3 different alleles. And they're showing the recessive being very light, the dominant being very dark, and then across the heterozygous for the 3 alleles, crossed with another heterozygous, and what you would get, if you were to count these up, that's 8 by 8, which should be 64, then you start getting these fractions of 64. The homozygous recessive for all 3 traits, relatively rare, 1 in 64, and the very, very dark homozygous dominant, big double A, big double B, big double C, that's 1 in 64. And then the range in the middle, much more common in the ratios and the fractions that you see. And here's a graph showing the same effect. The very, very light, the very, very dark would not be as common in the population. The middle would be more if you have a mixing of the hybrids. And interestingly, historically, people have tended to separate based on skin color, on religion, ethnicity. Interesting time in history as people have tended to intermarry both with religion and skin color, and mixing around the globe with the global travel and jet travel. people will move away from their